dA, total flux we want. Therefore, magnetic flux phi b integral A to B. Is that okay to you, sir? Because this radius is A, the outer radius is B, only then you will be able to take both A to B, mu naught I by 2 pi r into dr. Is that okay to you, sir? Mu naught by 2 pi is a constant. Mu naught by 2 pi is a constant. I is also a constant. R, you have integral A to B dr by r. Am I right, sir? Integral of dx by x is log x. Therefore, I get this as mu naught I by 2 pi into log to the base e, upper limit by lower limit. Upper limit is b minus lower limit a, and therefore I write it as b by a. Is that okay to you, sir? Or I will write it this way. I will write it this way. Mu naught I by 2 pi log to the base e r between the limits a to b, or I will write this as mu naught I by 2 pi into log to the base e b by a. Is that okay, please, sir? This is the flux, sir. This is the flux, total flux that is passing to the area ABCD. And when current varies, flux will vary. Therefore, I write when I varies, flux will change. Okay. When flux changes, will give rise to induced EMF. When I varies, flux will change and hence gives rise to induced EMF. I write induced EMF E as equal to minus d phi by dt. Okay. Now this is equal to minus mu naught I by 2 pi into log to the base e b by a. I is a variable again. Therefore it is di by di by dt. Is that okay to you, sir? I is a variable, sir. Therefore mu naught by 2 pi log to the base e b by a di by dt. Now, if you look carefully at this expression for E, this is similar to minus L di by dt. This is similar to minus dl by dt. Now, we need to compare these two equations. Okay? Comparing, if I give numbers to this, I will call this as equation number 1. This as 2. Therefore, I will say comparing equations 1 and 2. This L will be equal to mu naught by 2 pi log to the base e b by a. That will give me the expression for coefficient of self-inductance of two coaxial cylinders. Coefficient of self-inductance of two coaxial cylinders is given by the expression mu naught by 2 pi log to the base e b by a. Is that okay to you? Because L is not there, length, we can also say this will be self-inductance of the two coaxial coils per unit length. This is coefficient of self-inductance of two coaxial cylinders per unit length. For a length L, you have to multiply by L. As simple as that. As simple as that. Is that okay to you, sir? If this is okay to you, we move on to the next topic for discussion, which is determination of coefficient of self-inductance of a toroidal coil of rectangular cross section. Shall I rub this off? Toroidal coil of rectangular cross section. Let me first draw the diagram. Please see how I draw it carefully. Okay. This is how the magnetic field is entering. These are the turns of the toroid. Okay? Turns of the toroid. Now let us draw a few things here. Okay. The outer radius, I will mark it as B. Okay? That is A. I will take a small element here. Okay? The thickness of this element, let us take it as dr, and from here And from here, let us suppose this element is at a distance r. I will tell you about this, don't worry sir. Very interesting topic. Okay. We proceed to see how to calculate the coefficient of self-inductance of a toroidal coil of rectangular cross section. In the figure, I have shown you a toroidal coil rectangular cross section. This is a toroidal coil of rectangular cross section. Let n be the number of turns uniformly distributed over its circumference. I repeat once again, what is shown in the figure is a toroidal coil of rectangular cross section. Let n, capital N, be the number of turns uniformly distributed over the circumference of this toroidal coil. A is the internal radius of the toroidal coil. B is its external radius. A is the internal radius of the toroid. B is its external radius. I repeat once again, what is shown in the figure is a toroidal coil of rectangular cross section. N is the number of turns uniformly distributed wound over the circumference of the toroid. A is its internal radius. B is the external radius of the toroid. As you can see in the figure, the magnetic lines of forces are concentric circles. The magnetic lines of forces of this toroid are concentric circles. The magnetic lines of forces of the toroid are concentric circles as has been shown in the diagram. We are considering a circular path of radius small r of this toroid. We are considering a circular path of radius r of this toroid. Let the current flowing through its windings be I. We are considering a circular path of the toroid of radius r, the current flowing through the windings of the toroid be I. So we use Ampere's circuital law to determine the value of coefficient of self-inductance of this rectangular toroid from Ampere's circuital law. Okay, I will write line integral of magnetic field is equal to mu naught times total current passing. Current enclosed by the path. This you have studied in class 12 itself. Line integral of magnetic field is equal to mu naught times current enclosed by the path. Now if you integrate this, B, you have taken a radius r, circumference will be 2 pi r is equal to mu naught, the current through each turn is I, there are n turns into I. Sir, current flowing through each turn is I. There are n turns bound in the toroid, and therefore Ni will be the total current enclosed by that path. Okay. From this, I can write B is equal to mu naught Ni upon 2 pi considering okay, H. I am considering a rectangular strip of width dr, height h, at a distance r from the center. I repeat, what I am trying to tell. I am considering a strip of width dr, its height is h. Where is it? It is at a distance r from the center of the rectangular toroid. I repeat once again. We consider a rectangular strip of width dr, height h, at a distance r from the center. We want to calculate what is the magnetic flux linked with this elementary strip. The magnetic flux linked with this elementary strip. Sir, d phi b will be equal to b into area. Is that okay to you? What is the area? This is b is mu naught ni upon 2 pi r. Length into breadth will give you area. Therefore, height is h, thickness is dr. Therefore, I write it as h into dr. Is that okay to you, sir? If this is the magnetic flux linked with the elementary strip, we need to find out what is the flux linked with one turn of the toroid. Flux linked with one turn of the toroid. If I integrate this expression, I will get phi b is equal to integral d phi b between the limits b to a inner to outer radius. This will be mu naught ni h upon 2 pi integral a to b dr by r. Is that okay to you, sir? Therefore, I get phi b is mu naught ni h upon 2 pi log to the base e b by a. I have substituted the limit as well. I am getting this as my flux through one turn. So what is the total flux? Total flux. When there are n turns, total flux will be equal to n phi b. This will give me mu naught n square I h upon 2 pi log to the base e d by a. This will give me the total flux. Is that okay to you? Is that okay to you? Once I have got total flux, this is total flux. Flux can also be written as L into I. This is L into I. Let me call this as equation 2. Let me call this as equation 1. I will write the equation 1 here. Phi b is equal to mu naught n square hi h upon 2 pi into log to the base e d by a. Now you need to compare these equations. When you compare, you can see that comes to L. Therefore, I will write L is equal to mu naught n square h upon 2 pi log to the base E V by A. That is the expression for coefficient of self-inductance of a toroid having rectangular cross section. Is that clear to you, sir? All these are very important. As you can see here, we have taken Ampere's circuital law to find out what is the magnetic field and the magnetic flux linked to the elementary surface. Then we have calculated what is the flux linked with one turn, then total flux, then equated with phi is equal to Li. We end up with the expression for coefficient of self-inductance. Is that okay to you? Now, if that is clear to you, let me rub this off